We were looking at how to find probabilities for a standard normal random variable using the z-table. Here we said the z-table that we're using only has CDF values for positive values. And by CDF values, we mean we only have probabilities in the form probability capital Z less than equal to small z, and this is for only positive values of small z. For negative values, we'll use the symmetry property of normal distribution, where we know it is symmetric around its mean. Where for standard normal random variable, this means it's symmetric around its mean zero. And here we said there's a two-step process that we're going to use when we're going to try to find the probability of any standard normal random variable using the z-table. First, if there's any negative values, we're going to use symmetry property for that. So in the first step, we're always going to make sure we only have positive values in z. Right, so the first step is to ensure that you only have probabilities involving positive values. So you're basically finding, so basically you're making sure that you only have positive values in the first step. The second step is, once you only have positive values of z, if any probability is of the form probability z is greater than some positive value, then we'll write it in terms of CDF. Because remember, the table gives us CDF values for positive values of z. So the first step is to ensure we only have positive values of z. The second step is to ensure that's in the form of CDF. For the first step, we can use complement rule. For the second step, we can use symmetry property. Right? So we looked at two parts where we found probabilities to the left of the z value. Right, so we did these two. Now what we're going to do is we're going to find probabilities to the right of the z value. So finding probabilities to the right of the z value. Here we look at two parts again. So the first part is we want to find the probability z is greater than equal to 1.96. So like we said, the first step is always to show you only positive values of z. So here we do have a positive value, so that's not the issue. But the issue here is that it does not have a, it's not in terms of the CDF. So in the first step, you always intro your positive value Z. Yes, you do have that. Once you intro your positive values of Z, then you see whether your probability is in the form of CDF. It's not, right? And you know, Z table only has CDF values, right? Positive values of Z. It's a positive value, that's fine, but it's not in the form of CDF. The Z table only has CDF values of Z. So rewriting this in terms of CDF of Z. So we'll rewrite this in terms of CDF of Z, and for this we'll use a complement gives you, which we can then read from, which we can then read from Z table, because the Z table has CDF values for positive values of Z. Right, so here if I plot this, right, so essentially what we're finding, this is rho, this is so essentially finding the probability Z is greater than 1.96. This is the area we're interested in, right? This area is the probability Z is greater than 1.96, right? So now I want to find the probability Z is greater than equal to 1.96. Now, you know, this, although we do have a positive value Z here, right, but it's not in terms of CDF for Z. So what we're going to do is we're going to rewrite it in terms of CDF for Z. This area, which is probability Z is greater than 1.96, can be written as 1 minus probability Z is less than 1.96 using complement rule. Right, and so 1 minus probability, this is essentially the definition of CDF for Z, because remember, for continuous random variable, it doesn't matter whether you write it as probability Z is less than 1.96 or Z is less than equal to 1.96. The equal to sign does not matter, because for a continuous random variable, the probability takes a specific value 0. And we know for standard normal random variable, we express the PDF as phi like this rather than X. So this is 1.96, right? This is just essentially how we denote the CDF of a standard normal, this is how we denote the CDF of a standard normal random variable using phi rather than F. Right now, this is in the form of CDF of positive value Z, so this can be read from Z table. So we can read this from Z table, and we already found its value, but let's look at it again if you want to read it from the Z table. Now, if I want to read this from the Z table, so here we know the value Z that we want is 1.96. So 1.9 read from here, and the second decimal place we can read from here 1.96. So this is 0.975, right? So this table that we're using is giving us CDA values or positive values. So you read the up to the first decimal place, you read from here the value, and then the second decimal place is read. So 0.975, right? So going back to this. Yeah, so going back to this, we read this form as 0.975. So this is 0.025. Now let's find another probability. Now let's say we wanted to find the probability Z is greater than equal to minus 1.96. Earlier we found probability Z is greater than equal to 1.96, now minus 1.96. Remember, whenever you want to find probabilities for any standard normal random variable using the Z table, the first step is to ensure you only have positive value. So this is not a positive value Z here. So use symmetry property for any negative values. Negative values. So whenever you're finding probabilities of a standard normal random variable using the Z table, always include only the positive values of C first. If you don't, first use the symmetry property and then ensure that probability is in the form of CDF. Let's see how this area is. If I plot this, this is 0. So this is like minus 1.96. This is essentially the area we're interested in. This is the area is equal to probability Z is greater than equal to minus 1.96. Now we know the normal random variable is symmetric around its mean, which for a standard normal random variable means it's symmetric around 0, right? So the probability Z is greater than 1.9, Z is greater than equal to minus 1.96 by symmetry is the same as this area. The area probability Z is less than equal to 6, right? So basically by symmetry, we know because the normal random variable is centered in symmetric around its mean 0. So the probability that Z is greater than minus 1.96 is same by symmetry as the probability Z is less than 1.96. So by symmetry, because see the first step is always if you have any negative values in Z, you rewrite it back in terms of positive values of Z using symmetry property. So we can write this as probability Z is less than equal to 1.96 by symmetry. After you have it in terms of positive values, you see whether it's in the form of CDF or not. If it's not, then you write it in the form of CDF. But here it's already in the form of CDF, right? So this is just simply 1.96, right? This is already in the form of CDF of C. And this we know we can read from the table because this is just the CDF value, positive values, right? Read from Z table. This can be read from the table because remember the table we're using has CDF values of positive values. And we already know what 1.96 is. We just found it here as well. This is 0.975. Right? So this is just 0.975. So whenever you're finding probabilities for a standard normal random variable using this table, just first always keep in mind that first always make sure you only have positive values of Z. For any negative values of Z, we'll use the symmetry property. And once we have only positive values of Z, if the probability is not in the form of CDF or Z, you have a probability of the form probability Z is greater than some positive value, then make sure to write it in terms of CDF. Again, we follow this two-step process because the table we're using only has CDF values or positive values.